Mr. Dan here, and got a review video for you about reaction rates. This is from chapter 16 in your textbooks, so if you want to follow along with that or do some fun reading, go right ahead there, okay? So let's get into it. Here we got these elephants, and the purpose of the elephants is to remind us that we did that elephant toothpaste experiment back when in our lab for this, so I couldn't find any good pictures of an elephant toothpaste, so I found lots of good pictures of elephants. So I hope you like that. All right, whatever, that was weird. Let's go. So first thing we need to talk about is kinetic molecular theory. Okay, if you recall, this is kinetic is movement, molecular is molecules or particles, matter, and theory is explaining how. Okay, so the kinetic molecular theory is an explanation of how chemicals or matter moves. Okay, so a few basics about this. We'll say that matter is in constant motion, constant random motion at that. Particles of matter have energy, and when those particles of matter collide with each other, those collisions are said to be elastic, which means that there's no gain or loss of energy in the collisions between particles. And then as those particles have energy, they all have different energy. So the average kinetic energy of a substance is its temperature. Remember, temperature isn't really a thing. It's just a scale of how fast or slow certain things are moving. Okay? And then last, there's space between particles, and there's attractive and repulsive forces between particles as well. And this spacing and forces, it varies from one type of matter to another, and that's really based on what atoms we're talking about, what elements are present, and what condition those elements are held under. Okay, and so like, considering the kinetic molecular theory, we can do things like explain why certain types of matter are in a particular state. For example, why are solids solid, liquids, gases? Why are they all in that state of matter? And what happens when they change states of matter? We can use the kinetic molecular theory to explain all of that. So here, just a little diagram. You guys can check these out a little bit more and play when you look at this presentation on your own. But if you click on this image here, it's going to take you to a simulator. It's going to just show you, like this one, for example, shows us the random constant motion. And so what you want to do is just come down here and click play, and that's going to set all the particles in motion. You can see how crazy they're moving. And you can speed them up if you want to, or slow down. And what we want to do is click on trace a random molecule. So that's going to turn one of them red. And now we're just going to see the path that it takes as it bumps around with all the rest of these particles. And so you can see it's quite random. And sometimes it goes fast, sometimes it goes slow, sometimes it appears to not go anywhere. So I could stare at this for hours. I won't, because I'm recording right now. But it's worth checking out and just getting an idea for how that's supposed to work. And then if you recall this diagram that we made in class, we talked about it many times in the first semester. This is still useful for us here, as it's showing us just the different forces of attraction and movement as we go from solid, liquid to gas. We see how the motion and the attractive forces are changing as we change states of matter. The amount of energy and the temperature is increasing. The potential energy in bonding is decreasing as we melt and evaporate through the states here. And you can click on this one too. It'll take you somewhere, a similar one. And in this, we can take a look. Here's what it looks like if we have really strong forces. And then we can weaken those forces. And so think about what's going on with the spacing of the particles and the attraction between those particles as we change this. What factors could you change in order to make this happen, right? If we want to go from this really rigid shape to this really loose shape, what are some environmental conditions that you could manipulate in order to cause such a change? Okay, so let's move on to the next thing, which is going to talk about collision theory. Collision theory, it explains how different reactions occur at different rates. And the rules for this are really pretty simple. We just have to have particles that collide, and they have to collide with enough force or enough energy to cause a change. So chemically speaking, that means making and breaking bonds. And then they must collide facing the right direction so that that new shape can take place. So go ahead and watch this video. We watched it a while back. Watch it again, and it's going to talk about these principles of the collision theory, and then it's going to get into how we can manipulate these rules to either speed up or slow down a chemical reaction. Some of the things that we can do are highlighted here and on the next couple slides. I'll let you read them, but I'll give you some pointers as we go through. First, I'll say there's a few links over here that you could follow. It'll take you to pages that have good reading, some diagrams, and some simulations that might show you exactly how these factors work. Okay. The factors here, so starting with collision theory, and they have to collide. We have increasing concentration, increasing temperature, or really it's just changing concentration. Concentration up means reaction rate goes up. Concentration down means reaction rate goes down, right? Changing temperature, changing surface area, changing the pressure, that's one we didn't talk about before. But now that we've done gases, we can understand this a little bit more about how changing pressure will increase or decrease the reaction rate. And then we've got catalysts. And I'll talk about this one for just a moment here. The catalyst we're looking at here is enzymes, which are biological, as opposed to inorganic catalysts. The difference between the two would be when we did the elephant toothpaste, for those of you who used potassium iodide, that's an inorganic catalyst. For those of you who used yeast, that is an organic or biological catalyst. Both of them did the same thing, and they had very similar results. But I like the use of the enzyme here because it shows us, especially in this diagram, shows us some important features here. For one, we can see the substrates, which is how we say reactants when we're doing biology. So we have these two reactants, the red and the yellow. And if you notice the shape of them, you can see they're designed to fit together. You can see if we look at the product, when they fit, they'll make this nice circle shape here. But there's only one orientation that they will fit in that will create that product. So they have to line up in a very specific way. That's part of the collision theory, right? So they have to collide, and they have to collide in a specific direction. The enzyme here has a very specific shape in it that's going to allow for these two substrates to bind with it. And then once those happen, it'll cause a chain reaction of chemical reactions that will bind these two together. The enzyme will provide the energy needed to combine these two chemicals and produce this circular product that we have in the end. So this is just an example of a catalyst being done through an enzyme here. Okay. So to close this out, I want to talk about how we can look at these in graphical form when we take our test. I will ask you questions about these different factors for sure, and then I'll also ask you about how they're related to something like these graphs that we're going to look at. So this first graph shows us, we'll take a look here in the top left. This graph here is showing us a thing called activation energy. And in order for the reaction to take place, we have to increase the energy of the reactants high enough so that the reaction will take place. This is an exothermic reaction. As you can see, the energy level goes down, but it can't take a straight line, right? It's got to increase before it can start. Once we get it high enough, then that energy will carry the reaction all the way to the finish. But you've got to start it first. Right? Think about an example of this, maybe just like a candle for your birthday cake. The candle has the wick, and there's oxygen in the atmosphere. That's all that we need for the reaction. But you've got to get the wick hot enough first in order for that combustion reaction to take place. That's this process right here. Okay, so we've got to increase the energy. That's activation energy. We can speed up a chemical reaction now by decreasing the activation energy. That's the job of an enzyme or a catalyst. Okay? Its job is to decrease that activation energy. So here we can see by adding that enzyme, the activation energy is much lower here than it is without the enzyme. The final energy is the same with or without the enzyme, but the activation energy is much lower, so the reaction can proceed much faster. You can do this with an endothermic reaction as well. In that case, the final energy would be higher than the starting energy. This graph is one that we looked at in class also, and it's a bit, you're going to have to study this graph a little bit, but you're going to see it again when we do a test. This is called the Maxwell-Boltzmann distribution, and what it's showing us is, well, we're looking at the molecular speed or kinetic energy, and we're comparing that to a number of particles present. And so we've got the same sample held at two different temperatures, at a colder temperature and a warmer one. We see that there's a spread of temperatures. Here for the colder, it goes from almost 0 up to about 1,000. And then for the warmer one, it goes from almost 0 up to, oh gosh, it looks like almost 2,000 here. Okay? So the spread shows us that there's an average, okay, and we see the averages highlighted here at the peak, where the most probable speed, or where most of those particles are hanging out. Okay, so that's kind of what it's showing us, right? The height shows us how many particles there are at a particular temperature. What this red dotted line here represents is the amount of energy that's required for a chemical reaction to take place. The particles that are represented in the graph to the right side of this red dotted line all have sufficient or enough energy for the reaction to take place. It's a relatively small number. Everything to the left has insufficient energy. There's not enough energy for the reaction to happen. Most of them are on the left side. All of the colder sample is outside of the range where a reaction can happen. There are no particles that can react. And some of the warmer ones can. So a question that you might want to consider for the test is, what could you change about this in order to increase the number of reactions that take place? What could you do to increase the total yield of your reaction, or how could you end up with more products? Think back to the list of stuff that we looked at, right? We've got enzymes. What would it look like if you added a catalyst to this graph right here? What would change about this graph if we added a catalyst, if we reduced the amount of energy that you need to have a reaction? What would happen if we increased the overall temperature of the chemicals? How would the graph look different if we increased the temperature? How would the graph look different if we increased the concentration? So these are questions that I want to ask you, and I want you to think about those so that you can answer them on the test. We can talk about them, but for the purpose of the video now, I'm not going to answer those questions right now. Okay, one more graph to look at and then I'll let you go. This one just shows us about concentration over time. So here we're looking at a chemical reaction. The red ones are the reactants. The blue ones are the products. And we see one is increasing, one is decreasing. So as the reactants get used up, we start off with a lot of reactants. And as they get used up, we start creating more products. Okay, so that makes sense. But look what's happening at the end. How does the left or the right side of the graph over here, how does that compare with the left side? How does the angle of the graph change as we go from the left side to the right side? So that's another question that I'm going to pose for you right there. How does the rate of the reaction change for the red line and for the blue line as we go through time? So that's all I've got for you guys today. Check out Flipgrid for other assignments or anything else popping up on Google Classroom. I hope to see you guys in our class tomorrow. Thanks. Bye-bye.